Hello everyone, welcome to the problem solving session for deep learning. I am Tanuka from ISC. So in today's session we'll first resolve the issue that we had in the PCA problem last week. Once done with that, we will move on to some more aspects of autoencoders and then some convolutional neural network based questions. So let us start with the PCA problem. I had some issues in the calculation last week because of which the answer was not coming as expected. So let us go through the problem once more. So here is the problem. It is saying that we have 4 sample points in 2D real space, 4, 1, 2, 3, 5, 4 and 1, 0. 4 sample points are there. We want to represent the data in 1D using PCA. So the question is to compute the unit length principal component directions of X, and then we have to choose which of the principal components PCA algorithm will choose if we just want one principal component to be chosen. So the samples that we have are the first step in PCA computation was to compute the mean of these data points. This mean will be used for computing the covariance matrix. So let us first compute the mean. Let's denote that by mu. The mean will come as 3, 2. As we also computed last week, the mean will come as 3, 2. Once we have the mean, next step is to compute the covariance matrix. The formula for covariance matrix will be 1 by n summation I equals to 1 to n xi minus mu transpose xi minus mu. So this is the formula which is the kind of sample mean of xi minus mu transpose into xi minus mu. So here we have 4 samples, so 1 by 4. For each of them I have to subtract the mean from the data point. The mean is 3, 2. So first I subtract 3, 2 from 4, 1. So the first data point after subtraction of mean I get as 1 minus 1. For the next point 2, 3, I have to subtract 3, 2. I will get minus 1, 1. And for 5, 4 minus 3, 2, we will get 2, 2. And lastly we have 1, 0 minus 3, 2. So minus 2, minus 2. If you compute this will become 10, 6, 6, 10, right? This we computed last week also. So we can simplify this to 2.5, 1.5, 1.5, 2.5. This is the covariance matrix for this data points. Now the next step is to find the eigenvalues and eigenvectors of this covariance matrix, and the eigenvectors will actually be the principal components. So we have to find the unit vectors along those principal components. So let us first find the eigenvalues. So for finding the eigenvalue, what we have to do is 2.5 minus lambda, 1.5, 1.5, 2.5 minus lambda. This determinant we have to make it equal to 0. So that becomes 2.5 minus lambda whole square should be equal to 1.5 square, or 2.5 minus lambda should be equal to plus minus 1.5, which will lead to lambda being either 4 or 1. So these are the two eigenvalues for this particular covariance matrix, 4 and 1. Now once we have these eigenvalues, the next step is to find the eigenvectors corresponding to each of the eigenvalues. So let's say first we consider the eigenvalue 4, lambda equals to 4. So the formula to compute eigenvector is, let's say eigenvector we denote it by V. So sigma V should be equal to lambda V. That's the eigenvector equation, right? So our covariance matrix is 2.5, 1.5, 1.5, 2.5. So let's say V I write as AB equals to 4AB. That means if I simplify it, 2.5a plus 1.5b is equal to 4a, 1.5a plus 2.5b equals to 4a, which also implies that 1.5b equals to 1.5a. if I take this term to the right hand side, so it will become 1.5a. Similarly, from the second equation, this one, I get 1.5a equals to equals to 1.5b. So both of these equations lead to a equals to b. So if a equals to b, then we can have the eigenvector as 1 1 along this direction. Since we need the unit vector along this direction, the unit vector will be 1 by root 2, 1 by root 2. Similarly, we have to compute the eigenvector for lambda equals to 1. So for lambda equals to 1, again we have 2.5, 1.5, 1.5, 2.5, let's say AB. Lambda is 1, so right hand side is only this. Again we need to expand the equations. So 2.5a plus 1.5b should be equals to a, and 1.5a plus 2.5b should be equals to b. This can be simplified as 1.5a equals to minus 1.5b, and from the second equation, same thing, 1.5a equals to minus 1.5b, which implies a equals to minus b. So the eigenvector we can take as 1 minus 1. So the unit vector along this direction will be 1 by root 2 minus 1 by root 2. So the two principal components we obtained, one is this 1 by root 2, 1 by root 2, which corresponds to the eigenvalue of 4, and another principal component is 1 by root 2 minus 1 by root 2, which corresponds to the eigenvalue of 1. So these are the two unit vectors along the two principal components. Now given these two components, if we need to choose only one principal component, we will choose the one corresponding to the higher eigenvalue. So we will choose the one corresponding to lambda equal to 4. That is, this particular eigenvector will be chosen and your data will be projected along this particular direction. So the answer
1 by root 2, how did you take, ma'am?
So the vector we got is just 1 1. So if you just take the unit vector along that direction, so each element you should divide by the magnitude of the vector. So magnitude of the vector is nothing by 1 by root over 1 square plus 1 square, which is root 2. So each element I have to divide by the magnitude to get the unit vector.
Okay.
So this was the correct answer, as we mentioned last week also, that 1 by root 2 will be the principal component which will be chosen. So I guess whatever doubt was there in the calculation last week, that is resolved now. If any of you have any doubt, you can put it now. Okay, so since it looks like it's clear to everyone, so let us move on to today's topics. So today we will discuss some of the ideas of autoencoder, and then we'll solve one problem on convolutional neural network. So let us first look at the autoencoder questions. So the first problem says select the correct option about sparse autoencoder, where the first statement is sparse autoencoders introduce information bottleneck by reducing the number of nodes at hidden layers, and second is the idea is to encourage the network to learn and encoding decoding which only rely on activating a small number of neurons. So can any one of you answer which one is the correct option in case of sparse autoencoder?
Both are correct.
Okay. Any other option? Statement 2, is it you were saying?
Yes, ma'am.
Yeah, that's correct. Only statement 2 is correct, because in case of sparse autoencoder, the number of nodes in the hidden layer, that is not necessarily less than the actual input dimension. You can have lower as well as higher number of nodes as well in the hidden layer, but you ensure you are getting a compressed representation or a dimensionality reduction just by ensuring that a small number of neurons are only activated. That ensures that you have a compact representation even if you have the number of nodes in the hidden layer higher. So you can have any number of nodes in the hidden layer, but what you have to ensure is the representation, the activation of those nodes are sparse. There is only small number of neurons among the hidden layer ones are activated. So only the second statement is correct in case of sparse autoencoder. Now the next one is denoising autoencoder. Same question, we have to say which one is correct. The first one is the loss is between the original input and the reconstructed from a noisy version of the input. And second statement is denoising autoencoders can be used as a tool for feature extraction. So you have to choose the correct option.
A, statement A.
Yes, statement A is of course correct, but along with that statement B is also correct, because any of these autoencoders you can use as a tool for feature extraction. So when you are learning a denoising autoencoder, you have a noisy version of the input fed to the network, and you try to reconstruct the original output. In doing so, you learn a latent representation which you can use as a feature also for this. So both you can use it as a feature extractor, as well as the idea is you are trying to reconstruct from a noisy version of the input, and you are trying to minimize the loss between that reconstructed version and the original input. So both options are actually correct. Now let us look into contractive autoencoders. So we have to again say which of the following is true for contractive autoencoders. So any answer from anyone? So three options are there, actually four. So the first option is, in case of contractive autoencoder, we penalize the instances where a small change in the input leads to a large change in the encoding space. Second option is, large change in the input leads to a small change in the encoding space. And third is, small change in the input leads to a small change in the encoding space. In which case you penalize?
Statement 3.
Statement 3, you penalize.
It is 3.
Penalize instances where a small change in the input leads to a small change. Not really.
First one, madam.
Yeah, correct. First one is the correct option. So in case of contractive autoencoders, what we want is, whichever inputs are similar, those should lead to a similar representation at the hidden layer. So whatever is the input representation, if we make a small change to it, so those two representations are kind of similar. So those two should lead to similar latent representations at the hidden space. So if there is a small change in the input, a small change should happen in the latent representation also, in the encoding space also. So you penalize only when there is a small change in the input, but that leads to a large change in the encoding space, because we do not want that. So we penalize those instances only. And the third option, which is a small change in the input leads to a small change in the encoding space, that is what we want in case of contractive autoencoder. So we do not penalize when small change leads to small change. When a small change leads to a large change, then we penalize those instances. Okay. Now the next one is, which of the following autoencoder methods uses a hidden layer with fewer units than the input layer? Overcomplete, undercomplete, sparse, or denoising?
Sparse.
Same thing. So as I said, in case of the sparse autoencoder do not need the number of hidden layer units to be lesser. It can have equal number as the input dimension or even larger. You just need to ensure that only small neurons are activated, but there can be more neurons as well. So sparse is not a case where you necessarily need fewer units in the hidden layer. So that's not a correct option.
Undercomplete design. Undercomplete design.
Yeah, undercomplete is actually the correct option. So undercomplete necessarily needs that your hidden layer should have fewer units. So overcomplete will have more units in the hidden layer than input layer, and denoising also, it can have any number, that not necessarily. Now the last one from autoencoder. So here three sets of images are there. The first row shows the original images. The second row is a noisy version of the first row, and third row is what we want to reconstruct from the second row. In this case, which particular type of autoencoder should you use if you want to get this from this?
Denoising autoencoder.
Perfect. Denoising autoencoder. We are just having a noisy version of our actual input, and we are trying to reconstruct the original input back from the noisy version. So we should use a denoising autoencoder in this case. Okay, so this was all about the different types of autoencoder ideas. I hope the different types are all clear to everyone. If you have any doubts, you can put it in the chat or you can just unmute and ask. I'll wait for 2 minutes, then we'll move on to the next topic. Sujitra is asking sparse autoencoder. I don't have the concept clear. So, Sujitra, in case of sparse autoencoder, the idea is you have some input which you are passing through a number of hidden layers, and in the in autoencoders, what is our basic aim? We just want to learn some representation which is kind of compact representation and which can be useful for some other applications. So, we basically pass the input through this autoencoder, and at the middle of the network, so let us say this is the input you have. You just pass it through some hidden layers and you get a compressed representation after a few hidden layers. This representation is what we want. Then again we go back to the original dimension by increasing the dimensionality. This is the general autoencoder idea. In case of, so the idea is we have to have some compact representation in the latent space, in this space. Now, this compact representation you can achieve in different ways. So, in case of under-complete autoencoder, how we ensure that it will be a compact representation, that we reduce the number of neurons in this particular layer. So, we force that the representation that we'll get will be some lower dimensional than the input dimension. But in case of sparse autoencoder, we do not do that. So, in case of sparse autoencoder, we can have any number of neurons in this particular layer. You can have equal number as the input, or even you can have higher number of units in this hidden representation or latent representation. But the idea is when your input passes through these neurons, the activation that you get, that activations should be small for most of the neurons in all cases. So, in case of sparse autoencoder, you have a lot of neurons in the hidden layer, but you are not activating all of them. You are just activating a small number of them, all others are not activated. So, they will give a very small value as the output. So, the representation that you get, that might be higher dimensional, but most of the elements in this representation will be almost zeros. So, you get a sparse representation of the input. And to ensure, how do you do that? So, at each hidden unit, you just specify that what should be the probability of that unit being activated. So, you just try to minimize the KL divergence between the actual distribution of activating and non-activating and the fraction and the distribution that you want, that only this much number of times it should get activated, this much fraction of times it should get activated. You try to match those two distributions and try to activate minimum number of neurons in the hidden layer when you pass any input. So, your representation becomes 0 in most of the places, most of the dimensions.
Okay, but what is the difference between this and the normal autoencoder then, ma'am? There also the same thing is happening here. We are not activating some of the neurons, then the result is the same, right?
Yeah, the final motive is the same, but how we are achieving that is the difference. So, in case of,
we can activate some neurons, is that the?
Yeah, so in case of sparse, you are just not activating all the neurons, you are just activating a small number. But in case of the general one, which is the under complete design, there we do not put that constraint of not activating that KL divergence, we do not minimize, we just have the loss function as the like you have to reconstruct the mean square error between this reconstructed output and this input. That is the only component in the loss function. So, you are not imposing any constraint on the activations, because you have already reduced the number of neurons in the hidden layer, and it does not matter if all of them are activated also. But in case of sparse, you are adding another component in the loss, that I need these networks to be small, only a small fraction to be activated. So, the loss function is different in the two cases.
Yeah, okay, got it. Thank you.
And another question I got from Pooja is, what is stacked autoencoder? So, in case of stacked autoencoder, this is basically the layer by layer pre-training that we do. So, we have let us say we have this input. First, we just take one layer of neurons, one hidden layer, and we try to reconstruct back the output, the same input. So, yeah. So, we try to minimize the error between these two and try to train this one particular layer. Now, once the training is done, we fix this layer and we add one more layer from the autoencoder, and we reconstruct back the input, but this time we try to reconstruct back this particular representation. So, we try to minimize the error between these two, and we try to train this particular layer. Like that, we train on the entire encoder portion. Let us say encoder had 3 layers. So, all 3 layers we train this way. Now, once all these 3 layers are trained, so we have some pre-trained weights for all these layers. For the decoder part, we simply take the transpose of these weights to generate the decoder portion. And once we have this particular setting, now we fine tune the entire network as an end-to-end fashion. We try to minimize the MSE or some error between these two. So, you just keep on adding one, keep on training one layer and stacking those up. That is the idea.
Yes, ma'am. Got it. Thank you.
Yeah.
Madam, I have a question, madam.
Yes.
Madam, here deep learning network, it learns the features from the network, whatever it is there. And with the help of gradient descent approach, we try to update the weights. Is it only one approach that we have, like by using this back propagation learning, or any other methods are there for a network to learn?
Back propagation is just to back propagate the errors through the networks, but the way you optimize back propagation is the only way we use for back propagating the errors through the network. But whether we will use gradient descent to optimize the loss or any other optimizer, that can be different versions we can use. There are a lot of optimizers available, but this error propagation, all of them will use the back propagation idea only, because that is the basic chain rule we are using.
Madam, what is the advantage of non-linear activation functions?
So, it basically gives you a more more powerful network. So, if you just have linear activations, you can represent only a restricted number of functions. It can be just linear functions that you can represent, but there can be a lot of mappings that you need, which will involve non-linearities in between. So, there may not be a just linear relationship between the two. So, once you put these non-linearities at each level, it gives you a very powerful way of representing the mappings. So your network's capacity increases. So it can model a lot of mappings that only linear activation won't be able to model at all.
Okay. Madam, for all this image classification, image recognition, image segmentation, like clustering, for everything we have to use this only. Non-linear activation functions only we have to use.
So we in case the particular application that we are doing, that we know that the mapping is linear, and maybe in case of classification, if we know that the two representations at the two classes, the representations that we have for the two classes, in those representation space, these two features these two classes are linearly separable, we can use linear activation. But in most of the cases when we use image and all those high dimensional data, most of the cases it won't be the case that only linear activation will serve the purpose. So mostly non-linear are required.
Okay.
So let's proceed to the next part of our problems. So this one is a simple signal processing question that I had for the convolution part, just to start. So here we have to find the value of delta t minus 34 convolved with x t plus 56, where delta is the delta function and this star is the convolution operation. So can anyone tell me what will be the answer for this particular convolution? Just a simple signal processing question.
C3.
3. Yes, that's the correct answer. So let me just do it for others. So our signal is x t plus 56. If we just convolve it with the delta function, we get our signal back. If we just convolve with dt. Now what we are doing is we are doing a time shift in the delta. We are shifting it by 34. So that will have same shift in the output also. So our output, which was t plus 56, that will be shifted by minus 34. So the answer will be x t plus 22. This is because this is the linear time invariant systems property is this convolution. So the way input delta is shifted, similarly the output will also be shifted. So the answer will be x t plus 22. Correct. Now let us move on to the last problem of today's session. So this will be on convolutional neural networks. So let us first look at the problem. So we have a convolutional neural network. Suppose the input is a 31 cross 31 image with 3 color channels. So maybe the RGB image you can think about, it's a just 31 cross 31 image and you have the red, green, blue channels. Now the network has 2 convolutional layers. The first one has 50 filters. Filter size is 5 cross 5, stride is 2, and we are not using any zero padding. Then what would be the size of the first convolutional layer, or what would be the output of our size of the output of the first convolutional layer? So here our input dimension is 31 cross 31 cross 3. This is our input matrix shape, 31 cross 31 image and 3 channels. So total 31 cross 31 cross 3 matrix we will have. Now this we are passing through a convolutional neural network, one convolutional layer, first layer, that has 50 filters. 50 filters are there. Filter size is 5 cross 5 and stride is 2. and there is no zero padding done. We want to know the output shape. So, let us first look at the general formula of computing this shape. So, let us say I'll show the formula with one dimensional data. We can just simply generalize it to any dimension. It will be the same along each dimension. So, let us say this is the input layer you have. Let us say there are n units are there in the input layer. It's a, let us say, one dimensional data. So, n units are there, and let us say we are doing some zero padding on both sides. Let us say p number of units you are padding on both sides. So, total you have now n plus 2p number of neurons. Now, when you do this convolution, let us say you are using a convolutional filter with size, filter kernel size maybe some f, and stride is some s, let us say. So, what will happen is, first let us say if this f equal to 3, I am assuming for drawing this particular image, but we will write the expressions in terms of f only. So, let us say if f is 3, so this first 3 neurons will be first passed through the convolutional kernel, and it will lead to one value, one neuron in the hidden layer, in the next layer or the CNN layer. So, first these 3 are combined, your kernel will pass on these 3. Now, the stride is some s, let us say s is 2 for our image. So, the kernel will be advanced by 2 units. So, next the kernel will be placed from here to here. So, this initially the starting point was here, 2 steps it will go, these 2 steps. Now, the starting point of the kernel is here. Now, this and this will be combined through the kernel and will lead to one layer in the one unit in the next layer. Similarly, again the kernel will move by 2 steps and it will be placed here. These 3 will now combine to give you the next one. Similarly, this way as long as your input dimension goes, input number of neurons goes, this kernel will keep on striding through it. So, if we want to see how many numbers we will get here, so initially we have n plus 2p number of neurons. Okay. Among that, at the last step, the kernel should be able to combine f number of neurons, and before it reaches that, it will stride by 2 at a step. So, total number of steps like that will be divided by s. So, till n plus 2p minus f point the kernel can go, and it will go 2 step at a time. So, this many number of steps it can go. Now, you will have to take the floor, actually this many number of steps it can go, plus 1, which is for the last position of the kernel, when which contributed this minus f, when it is at the last position, that will give 1 unit. So, the total number of units in the hidden layer will actually be this n plus 2p minus f, where f is the kernel size, divided by s, where s is the stride, floor of that, plus 1, that will be the number of units in the convolutional layer output. Now, another thing is, this is just one kernel we passed and computed this. Like that, we can have a number of filters or a number of kernels. Here it says 50. So, each of those 50 filters will pass in the same way and lead to 50 set of this neurons in the second layer. So, in this particular case, if we consider, our input was 31 cross 31 cross 3, and our filter stride is kernel size is 5 cross 5, stride is 2, and as mentioned we are not using any zero padding. So, in this case along each dimension the output number of units will be floor of 31 plus 0 minus 5 by 2 plus 1, which becomes 14. This will happen in both the dimension, this 31, both way, because when you have a 2D input, let us say this is your image. So, your kernel will first be placed here, then it will go here and compute like this, like that, and the end it will compute like this. Once this row is done, it will again shift down by the same stride. So, if it is 2, it will now go here and it will compute this way again. It will keep on computing. So,
value get 0.
sorry.
How the p value gets 0?
So, in the question itself it is mentioned that we use no zero padding in this particular layer. So, I just ignored the p for this. P is for the zero padding that you are doing on each side of the neurons.
What is this floor, madam? Floor means what?
Floor means if you get a fraction, let us say 3.5, we will round it to the lower number, lower integer. Because it may not always be the case that we have a divisible number of units in the layer. So, in case we get a fraction, we will get the lower integer, round to the lower integer, because otherwise, so in this case only the image that I have drawn here, 1 unit is remaining. So, next if you again advance the kernel 1 by 2 steps, so now it will be placed here, but now the kernel cannot compute the output because it do not have 3 numbers. So, in this case you will get a fraction or something. So, in this case you should take a floor of that, and this dimensionality reduction will happen in both dimensions, both this 31 will go to 14. Now, initially you had 3 number of channels. So, your matrix was input matrix was something like this, you can say, and the kernel sat on this, let us say, and this, when you have a 3D input, this kernel actually combines the entire portion. One kernel will combine the entire portion and get one value. Again it will shift, combine the entire portion and get another value. Like that one kernel will do. Similarly, you have here 50 filters. So, all of them will do the same operation. So, that the first kernel, whatever it is computing, that let us say is the first 2D matrix. Then the second kernel, whatever it is computing in the same fashion, that will be appended at the at the third dimension. Like that, for each filter you will get one matrix. So, here this 14 cross 14 matrix, you will get one 14 cross 14 matrix for each of the 50 filters. So, total you will get 14 cross 14 cross 50. This will be the dimension of the first convolutional layer, 14 cross 14 cross 50 from 31 cross 31 cross 3, because you have 50 filters. So, this third dimension goes to 50, and this 14 you have to compute based on the filter kernel, stride, zero padding, all those things. Now, let us look at the next step of the question. So, now we know the size of the first convolutional layer, which says after the first convolutional layer we use a pooling layer with filter size 2 cross 2 and stride 2. So, let us see that. So, after CNN 1 we have 14 cross 14 cross 50. Now, we will do pooling on top of it. So, what happens in case of pooling? Similar thing, if you have, these are the neurons you have, and here your pooling filter size is 2 cross 2, stride is 2. I am again visualizing it for just 1D. So, you put the filter over here, you perform the pooling on using these 2 units. So, let us say you are taking max pooling. So, you take the max value of these 2, you get the output, you then advance the filter to the next position depending on your stride. So, here if the stride is 1, initially it was here, then it goes here. In case your stride is 2, then initially it was here, next it will shift by 2 places, it will be placed here. Depending on the stride, you should advance it, and again you take the max of these 2 and get this. So, in case of pulling also, what will be the number of neurons that you get? Initially, let us say you have n number of neurons, you have to have the n minus f by s floor plus 1. Similar calculation as the convolutional layer. Similar way you will get the output for this also. So, for you place the filter at one position, get output value for that using f units, you shift it by s units, which is the stride, again compute by f units. Like that you should keep on doing, that will lead to this number of neurons at the output of the max pooling. So, here we had the CNN output as this. If we do max pooling on this, what we will get is, so here our filter is 2 cross 2 and our stride is 2. Here also same thing will happen, both these axes will be modified in the same way. So, here we will get 14 minus 2, which is 12, divided by s is 2. So, 6 plus 1 7. So, 7 cross 7 cross 50. This will be the output of the first max pooling layer. Then the pooling layer is followed by the second convolutional layer. For the second convolutional layer, we are using 0 padding, so that the size does not change because of the convolutional layer. So, whatever convolutional layer we are using, after this we are using 0 padding appropriately, so that the dimension is not changed. So, your 7 cross 7 is remaining 7 cross 7, because you have appended the required number of zeros on both sides. But it is saying that this layer has 100 filters, each with size 3 cross 3 and stride 1. So, in case it has 100 filters, now your this 50 will get changed to 100. So, this will be your CNN 2 dimension. So, here you had 100 filters, each with 3 cross 3 size and stride is 1. Stride is 1. So, this is the dimension after the second CNN layer. Let us say we will compute this total number of weights a bit later. Let us just compute the network first, work out the network first, then we will compute these weights. So, it says after the second convolutional layer, we have another pooling layer with filter size 2 cross 2 and stride 2. So, after this again you have one pooling layer, same setting of this pooling layer. So, can anyone tell me what will be the output of this pooling layer, the size? We will use the same method as for the first pooling layer, because the specifications are same, 2 cross 2 filter with stride 2.
It's n minus f by s plus 1 itself, right?
Yeah, same thing.
No padding.
For pooling we never do padding, because in pooling we are anyway trying to reduce the dimension.
Yeah, yeah. Right.
Neelam is saying 1 cross 100. How are you computing 1? Can you just unmute and tell me what are the values you are using for this N, F and S?
Ma'am, I have a doubt. In a case of max pooling equation, what will be the n?
N is the number that you have at the input of the max pooling. So the CNN output that we had, this is the input to the, sorry, this one, this is the input to the max pooling, right? So at each dimension you have 7 units.
Okay.
So that will be the n for this.
Okay. Thank you.
So here our n will be 7 and f and s are 2. So the output dimension will be 3 cross 3 cross 100.
Very well.
So basically this 2 cross 2 kernel with 2 stride is generally used to half the dimension of the previous layer. Now this says after this then we have 2 fully connected layers. So this is a general structure of CNN based classifiers. So the output that you get, you just flatten these outputs. So at this point these are arranged as a 3D matrix, right? So 3 cross 3 matrices appended in the third dimension, 100 such are there. So it's a 3D matrix. We just flatten this entire matrix to get one vector whose length is 3 cross 3 cross 100, that is 900 dimensional vector, and we pass it through a fully connected layer. So here we are saying there are 2 fully connected layers. The first one has 20 nodes and the next one has 5 nodes. So first we pass it through.
One question. Where did we get this 100 from? Was it in the question itself?
So the question said this convolutional layer we use have 100 filters.
Oh, okay.
So that third dimension is basically the number of filters that we have.
So max pool also got it.
Max pool doesn't reduce the third dimension, it will just reduce the image size.
Right.
So now from this 20 we have another fully connected layer which is 5, and this gives us the final output. This is the entire network structure that we have. Now the other part of the question is what is the total number of weights we need to learn for the 2 convolutional layers, and what is the number of weights we need to learn in this entire network. So let us just work that out. So at the input you had 31 cross 31 cross 3, then you had a CNN. Now this CNN, in the first CNN you had 50 filters, each 5 cross 5. So 5 cross 5 filters, 50. Now this 5 cross 5 filter, what will be the number of weights? Let's say weights and biases both if we compute. So 5 cross 5 filter, this 5 cross 5 filter is same like a 2D matrix of dimension 5 cross 5, but it will also combine all the 3 channels of the image, right? It will also combine the 3 channels. So the number of weights that this kernel will have, so the weight that this kernel will have, that will be 5 cross 5 into 3. Each dimension will have 5 cross 5 number of weights. So total is this for one particular filter. Like that you have 50 filters. So total number of weights will be this into 50. This will amount to 3750. And if we consider the biases, each filter just has one bias term. So you have 50 filters, 50 bias terms. Now the next layer was a max pooling. After CNN we had a max pooling. Max pooling doesn't have any learnable weights. You are just taking the maximum of the inputs. So no weights or biases involved. Next is the second CNN layer which has 100 filters, filter size 3 cross 3. and the input to this particular filter was the third dimension was 50. So, these 3 cross 3 filters will combine over all those 50 matrices. So, the CNN2, which are 3 cross 3 and 100 filters were there. So, it will be 3 cross 3 cross 50. This many weights will be there for one filter. Like that you will have 100 filters, and since 100 filters, bias terms will be 100. So, this will amount to 45,000. So, these are the number of weights for the CNN layer. Now, after the CNN2, we have the max pooling 2, which also do not have any weights involved. After this, we are flattening the output and passing it through the fully connected layer. So, if we write the first one as FC1, that is taking a 900 dimensional as input, and it has 20 units in this particular layer. So, FC1 for this, the weight will be 900 cross 20. 900 cross 20 and bias terms are 20. This is 18,000. And then the last FC layer, which is going from 20 to 5. So, weights will be 20 cross 5, that is 100, and you will have bias terms 5. So, this is the total number of weights and biases present at each level of the network. I hope this is clear to everyone. If any doubts are there, you can ask. So, this is how we compute the dimensions for each CNN layer, max pooling layer, and the number of learnable parameters that will be there for this layers. So, these were the problems that I planned for today. If there are any doubts, we will discuss that, then we'll
Ma'am, that FC1 calculation once again.
Which one calculation?
FC1.
FC1. Okay. So, at the out, so this FC1 is after this max pooling 2, right. So, your max pooling 2 output, max pooling 2 output is 3 cross 3 cross 100. So, it is a 3D matrix. We cannot feed a 3D matrix to a fully connected layer. We have to flatten the matrix in a 1D array, and we will have to pass it to the fully connected layer. So, to flatten, we just stack up the columns or rows, any way we can stack up and just flatten it. So, once you flatten it, it becomes a 900 dimensional array. Okay. So, you have 900 units now, like that. And your FC1 first fully connected layer has 20 units. Here you have 20 units. So, what is the idea of fully connected layer? That each of these neuron will connect to each of the previous units through some weight. So, each of these 20 neurons will be connected to 900 neurons. Now, so number of weights involved for one neuron is 900. So, total there will be 900 cross 20, 18,000 weights involved. Is that clear to you now?
Yeah. Thank you.
Yeah. And for biases, each neuron we just have one bias involved. So, bias is only 20.
Ma'am, I've heard that changing the network architecture, that is changing the size of the hyperparameters as well as where each layer comes in,
Yeah.
we can improve the accuracy of the
Yeah.
output. So, what kind of changes can we bring in here? It looks like a set kind of pattern, right?
Yeah. So these architectures are completely experimentally developed mostly. So this since let's say you have a image classification kind of task, then we use CNNs mostly for extracting features from images. So you will have some number of layers of CNN. After that, since you need to go to finally one particular decision, we just stack up, or we can take average also over all dimensions, and we get a 1D vector which we convert to the single decision. So here you can, I mean, while tuning this architecture, we can try different number of filters, different number of layers. So if we have very less number of layers and the problem is very complicated, it may not be able to capture enough efficient enough features. So that we can try with different number of layers, different size of these kernels. We can at different layers we can put different size, so that different layer keeps on getting different features.
What
These
about
are
the frames, different frame filters? I'm sorry, filters that we use. Can we change this size in the sense?
so
Uh,
this that filter kernel size, which here we said ki it is 5 cross 5.
yeah.
This also we can change. We can change the stride also. All these parameters can be tuned. But we do not use a very large size of the filter, because that will kind of average out the characteristics over a very large region. These
Yeah.
3 cross 3, 5 cross 5, these are kind of standard well used numbers actually, but depending on the application, any other number also can be more suitable.
So basically, filters are used so that we can enhance the features, isn't it?
Yeah, right.
Okay, so we can create our own filter. How do we create the filter so that we have to enhance the certain feature or
So here entire thing is learned through the network itself. So we just fix the loss function, and this filter weights that will be there, the coefficients of this filter, those are learned here itself. So we do not specify, depending on the data and the task we have at hand, these filter coefficients will be automatically learned through the back propagation algorithm.
I see. Okay, okay, fine.
So this is basically the data driven way. Instead of so if you want to design the filter yourself, you will have to have the knowledge ki how to combine the values and how to get the feature. But if we do not have that idea for any particular application, we can go for this approach, where you just learn what should be the filter weights if you want
Filter.
to get that decision.
Right, right. Okay. Okay.
Yeah. Any other doubts from anyone? Okay, if no more doubts are there, we can close today's session here. Thank you everyone for joining. We'll meet again in the next week with few more problems on convolutional neural network. Thank you.
Thank you, ma'am.